Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 102, Meta-Learning by GPT-3 and a list of full proposals for AI alignment, published on the 3rd of June 2020 by Rohin Shah. Highlights. Link, Language Models are Few-Shot Learners by Tom B. Brown et al., summarized by Rohin. The biggest GPT-2 model, discussed in newsletter 46, had 1.5 billion parameters, and since its release, people have trained language models with up to 17 billion parameters. This paper reports GPT-3 results, where the largest model has 175 billion parameters, a 10 times increase over the previous largest language model. To get the obvious out of the way, it sets a new state-of-the-art on zero-shot language modeling, evaluated only on Penn Tree Bank, as other evaluation sets were accidentally part of their training set. The primary focus of the paper is on analyzing the few-shot learning capabilities of GPT-3. In few-shot learning, after an initial training phase, at test time, models are presented with a small number of examples of a new task, and then must execute that task for new inputs. Such problems are usually solved using meta-learning or fine-tuning. For example, at test time, MAML takes a few gradient steps on the new examples to produce a model fine-tuned for the test task. In contrast, the key hypothesis with GPT-3 is that language is so diverse that doing well on it already requires adaptation to the input, and so the learned language model will already be a meta-learner. This implies that they can simply prime the model with examples of a task they care about, and the model can learn what task is supposed to be performed, and then perform that task well. For example, consider the task of generating a sentence using a new made-up word whose meaning has been explained. In one notable example, the prompt for GPT-3 is, quote, "A watpu is a small furry animal native to Tanzania." An example of a sentence that uses the word watpu is, "We were traveling in Africa and we saw these very cute watpus." To do a fardaddle means to jump up and down really fast. An example of a sentence that uses the word fardaddle is, and then given this prompt, GPT-3 generates the following output. One day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardaddles. The paper tests on several downstream tasks for which benchmarks exist, for example question answering, and reports zero-shot, one-shot, and few-shot performance on all of them. On some tasks, the few-shot version sets a new state-of-the-art, despite not being fine-tuned on the benchmark's training set. On others, GPT-3 lags considerably behind fine-tuning approaches. The paper also consistently shows that few-shot performance increases as the number of parameters increase, and the rate of increase is faster than the corresponding rate for zero-shot performance. While they don't outright say it, we might take this as suggestive evidence that as models get larger, they're more incentivized to learn general reasoning abilities. The most striking example of this is arithmetic, where the smallest 6 models, up to 6.7 billion parameters, have poor performance, less than 20% on 2-digit addition. Then the next model, 13 billion parameters, jumps up to better than 50% on 2-digit addition and subtraction, and the final model, 175 billion parameters, achieves better than 80% on 3-digit addition and subtraction, and a perfect 100% on 2-digit addition, all in the few-shot regime. They explicitly look for their test problems in the training set, and find very few examples, suggesting that the model really is learning how to do addition. In addition, when it's incorrect, it tends to be mistakes like forgetting to carry a 1. On broader impacts, the authors talk about potential misuse, fairness and bias concerns, and energy usage concerns, and say about what you'd expect. One interesting note, quote, "To understand how low and mid-skill actors think about language models, we've been monitoring forums and chat groups where misinformation tactics, malware distribution, and computer fraud are frequently discussed." End quote. They find that while there was a significant discussion of misuse, they found no successful deployments. They also consulted with professional threat analysts about the possibility of well-resourced actors misusing the model. According to the paper, quote, "The assessment was that language models may not be worth investing significant resources in because there's been no convincing demonstration that current language models are significantly better than current methods for generating text, and because methods for targeting or controlling the content of language models are still at a very early stage." End quote. Rohin's opinion. For a long time, I've heard people quietly hypothesizing that with a sufficient diversity of tasks, regular gradient descent could lead to general reasoning abilities, allowing for quick adaptation to new tasks. This is a powerful demonstration of this hypothesis. One critique is that GPT-3 still takes far too long to identify a task. Why does it need 50 examples of addition in order to figure out that what it should do is addition? Why isn't one sufficient? It's not like there are a bunch of other conceptions of addition that need to be disambiguated. I'm not sure what's going on mechanistically, but we can infer from the paper that as language models get larger, the number of examples needed to achieve a given level of performance goes down, so it seems like there is some strength of general reasoning ability that goes up. Still, it would be really interesting to figure out mechanistically how the model is reasoning. This also provides some empirical evidence in support of the threat model underlying inner alignment concerns, discussed in newsletter 58. They're predicated on neural nets that implicitly learn to optimize. To be clear, I think it provides empirical support for neural nets learning to reason generally, not neural nets learning to implicitly perform search in pursuit of a MESA objective. See also, is the term MESA optimizer too narrow? Discussed in newsletter 78. Link: An overview of 11 proposals for building safe advanced AI by Evan Hubinger, summarized by Rohin. This post describes 11 full AI alignment proposals, where the goal is to build a powerful, beneficial AI system using current techniques, and evaluates them on 4 axes. 1. Outer alignment. Would the optimal policy for the specified loss function be aligned with us? 2. Inner alignment. Will the model that is actually produced by the training process be aligned with us? 3. Training competitiveness. Is this an efficient way to train a powerful AI system? More concretely, if one team had a reasonable lead over other teams, would they keep at least some of the lead if they use this algorithm? 4. Performance competitiveness. Will the trained model have good performance, relative to other models that could be trained? 7 of the 11 proposals are of the form recursive outer alignment technique plus technique for robustness, as discussed in newsletter 81. The recursive outer alignment technique is either debate, from newsletter 5, recursive reward modeling, from newsletter 34, or some flavor of amplification, from newsletter 42. The technique for robustness is either transparency tools to peer inside the model, relaxed adversarial training, as discussed in newsletter 70, or intermittent oversight by a competent supervisor. An additional 2 proposals are of the form non-recursive outer alignment technique plus technique for robustness. The non-recursive techniques are vanilla reinforcement learning in a multi-agent environment and narrow reward learning. Another proposal is microscope AI, in which we train AI systems to simply understand vast quantities of data, and then by peering into the AI system we can learn the insights that the AI system learned, leading to a lot of value. We wouldn't have the AI system act in the world, thus eliminating a large swathe of potential bad outcomes. Finally, we have STEM AI, where we try to build an AI system that operates in a sandbox and is very good at science and engineering but doesn't know much about humans. Intuitively, such a system would be very unlikely to deceive us, and probably would be incapable of doing so. The post contains a lot of additional content that I didn't do justice to in this summary. In particular, I've said nothing about the analysis of each of these proposals on the 4 axes listed above. The full post talks about all 44 combinations. Rohin's opinion. I'm glad this post exists. While most of the specific proposals could be found by patching together content spread across other blog posts, there was a severe lack of a single article laying out a full picture for even one proposal, let alone all 11 in this post. I usually don't think about outer alignment as what happens with optimal policies, as assumed in this post. When you're talking about loss functions in the real world, as I think this post is trying to do, optimal behavior can be weird and unintuitive in ways that may not actually matter. For example, arguably for any loss function, the optimal policy is to hack the loss function so that it always outputs 0, or perhaps negative infinity. Section Technical AI Alignment. Subsection Miscellaneous. Link Planning with Uncertain Specifications by Ankit Shah et al., summarized by Rohin. Suppose you recognize that there are no certain specifications, and so infer a distribution over specifications. What do you then do with that distribution? This paper looks at this problem in the context where the specifications are given by formulas in linear temporal logic, which can express temporal non-Markovian constraints. They identify 4 possibilities. 1. Most likely. Plan with respect to the most likely specification. 2. Most coverage. Satisfying as many formulas as possible, ignoring their probability, as long as they have non-zero probability. 3. Chance constrained. Like the above, except you weight by probabilities, and drop the least likely formulas up to a parameter delta. 4. Least regret. Like the above, but with delta set to 0. Intuitively, most likely won't be very robust since it's only taking one specification into account. Most coverage is aiming for maximum robustness, and chance-constrained interpolates, where larger delta corresponds to trading robustness for gain in ability. This is exactly the pattern we see in a task where a robot must set a dinner table. Rohin's opinion. Ultimately, I hope that in cases like this, the agent plans conservatively initially, but also tries to learn which specification is actually correct, allowing it to become more bold over time. Nonetheless, it seems quite difficult to do this well, and even then we likely will have this trade-off between robustness and task performance. This is the case with humans too. If you try to please everyone, robustness, you'll end up pleasing no one, task performance. Section Other Progress in AI. Subsection Reinforcement Learning. Link. Suffix. Mastering Mahjong with Deep Reinforcement Learning by Junjie Li et al. Summarized by Rohin. Mahjong is a large imperfect information game with complex rules where turn order can be interrupted. This makes it challenging to solve with existing techniques like MCTS and counterfactual regret minimization. This paper details what was necessary to build Suffix, an AI system that is stronger than 99.99% of humans. Some highlights. Like the original AlphaGo, they first learned from human gameplay and then fine-tuned using reinforcement learning, with deep CNNs as their models. They learned both action models as well as value models. They added an entropy bonus to ensure that the policy remains stochastic enough to continue learning over the course of RL. They have 5 learned action models, corresponding to 5 different decisions that need to be made in Mahjong, as well as a rule-based system for deciding whether or not to declare a winning hand. To handle imperfect information, they first train an oracle agent that gets access to all information, and then slowly reduce the amount of information it gets to observe. They could use search to improve the performance online, but did not do so in their evaluation, since Suffix was playing on a website with time constraints. Suffix with search would probably be significantly stronger. Rohin's opinion. I'm a bit curious how they removed observations from the oracle agent, given that you usually have to keep the structure of the input to a neural net constant. Perhaps they simply zeroed out the observations they didn't want? Link. Mastering Complex Control in MOBA Games with Deep Reinforcement Learning by Deheng Ye et al. Summarized by Rohin. This paper presents an AI system that can play the multiplayer online battle arena game Honor of Kings. They're inspired by OpenAI 5, discussed in Newsletter 13, and Honor of Kings sounds quite similar to Dota, though it's 1v1 instead of 5v5, and have a similar learning setup, reinforcement learning using PPO. Their architecture requires an off-policy algorithm. I'm not sure why, maybe they have stale parameters across their rollout servers, so they add an importance sampling correction to the PPO objective, as well as an additional type of gradient clipping. The input is a combination of the image and underlying game state info. The resulting agents are able to beat top human players, and in an event with the public, the AI system lost only 4 out of 2,100 matches. Unlike OpenAI 5, this required only about 100 hours to train, though it's unclear how much compute was used. Subsection Deep Learning. Link. More Efficient NLP Model Pre-Training with Electra by Kevin Clark et al., summarized by Flo. There are 2 main approaches to pre-training for NLP. Language models, LMs, which iteratively predict the next word in a given incomplete sentence, and masked language models, MLMs, which predict the identities of a few masked words in an otherwise complete sentence. While not just looking at the previous word, bidirectionality, can be advantageous, MLMs only learn to predict the masked words, which reduces how much is learned from a given sentence. The authors present an alternative approach, Electra, that outperforms Roberta while requiring less than 1/3 of the compute. This is achieved by changing the form of the pre-training task from predicting words to discriminating fake words. Instead of masking, some words are replaced by words generated by an MLM, and the trained model has to classify these as fake. This way we get bidirectionality, but also a more dense signal, as the model has to produce an output for every single word, not just the masked ones. While this looks similar to GANs, the generator is only trained on the usual MLM loss and is not incentivized to fool the discriminator, as GANs don't seem to work well on sequence data. Flo's opinion. I found it a bit surprising that replacing word prediction with fake discrimination would help that much, but from the ablations, it seems like this is really mostly an instrument to get a loss signal for every single word, which is a cool idea. On a more zoomed-out perspective, results like this seem to show that gains in algorithmic efficiency, as discussed in Newsletter 99, are not fundamentally slowing down. Subsection Hierarchical Reinforcement Learning. Link DADS, Unsupervised Reinforcement Learning for Skill Discovery, by Archit Sharma et al., summarized by Rohin. Reinforcement learning in robotics typically plans directly on low-level actions. However, it sure seems like there are a simple set of primitives, like walking, running, shuffling, etc., that are inherent to the robot morphology. What if we could learn these primitives and then plan using those primitives? This paper introduces a method for learning these primitives without a reward function. They simply optimize skills for predictability and diversity by optimizing the mutual information between the current state and the next state, conditioned on which skill is being executed. They can then use these primitives for model-based planning for a downstream task. You can think of this as a regular reinforcement learning problem, except that an action in their action space takes the form execute skill X for T time steps. They use Model Predictive Control, MPC, in which you sample a bunch of trajectories and execute the first action of the trajectory that gets the highest reward. Since each of their high-level actions determines the policy for T time steps, they can scale to much longer horizon tasks than MPC can usually be used for. They show that this approach is competitive with regular model-based RL. Rohin's opinion. I think unsupervised learning is likely to be key in getting more powerful and general AI systems without requiring a truly staggering amount of expert data, and this is a great example of what that might look like. Note, though, that the learned primitives are certainly not what you'd expect out of a human. For example, the humanoid learns to vaguely shuffle in a direction, rather than walking. In addition, they did require specifying an XY prior that required skills to be diverse based on XY coordinates, which is why the skills learned navigation primitives, as opposed to, for example, distinct types of flailing. This concludes Alignment Newsletter number 102. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.